Hi all. I decided to put up something kind of emotionally dark for the background here because, well, you know how it goes. Nobody really knows anything about how this is going to work out for us all. So, given that low note, let's switch back to the time series from the handbook where we can say something about GDP and learn some new statistics that perhaps I can go off and apply to some epidemic data tomorrow. So the video, or excuse me, not the video, the spreadsheet we had left off with looks like this, and I made some mistakes in it. Okay, so this is the regression that I did for case 4 where I said I'm going to fake it out a little bit, and you can see that because it's got these missing values right here. But what I did that was incorrect is I intended to do this from 1930 to 1996, and I labeled it as such, but if we look over here, I've got way too many observations. So I have done this from like 1931 to 2020 or something like that, and that's not what I wanted to do. I wanted to cut it off in 1996 in case we wanted to do any forecasting going forward. So I want to delete this sheet, redo it, okay, and then move on from there. So delete, that's easy, okay. If I go back to my data and go over a few rows, where I want to cut it off is 1996, which is row 79. Okay. Um, and I'm just looking at something here. Yep, 9.308. Yes, that looks correct. Okay, made myself a little nervous. Okay, so go up to data, data analysis, choose the regression tool, and now going to give it down to row 79 for the y variable, and down to row 79 for this column of ones. And then I'm not going to put anything in about the constant or anything like that. Excuse me, I'm going to actually, set the constant to be 0. Tell it I have labels. Okay, and click OK. And there's my similar regression to what I did the other day, but you can see right now it's at 67 observations, which is much better. So first thing I'm going to do, okay, is clean this up. I'm going to make everything wide enough to fit the labels. I'm going to center everything. I'm going to change the number of digits that I show to 3. And I'm going to add a label by hand up here. So regression of differenced logs of our GDP on an intercept. And that's 1931 to 1996 now. And so this is our case 4, and I'll label it as such. Oops, got a typo there. Didn't like that. Okay, now this is not really a good regression for Excel because we're faking it out, but the same arguments go through the other day. It's estimated the intercept correctly. The R-squared has changed substantially because we've changed the dependent variable. I'm fitting approximate growth rates now rather than log levels. And the standard error is in about the same range that it was before. Now, when I got after case 3, I created fitted values and residuals, and I want to do the same thing here. So I'm going to go back to this source data, but what I'm going to do is take this entire range here and bring it over. So this starts in H12. So let me go to here and make this equals data exclamation point H12. And then copy this down. Let me see. Probably going down to 87, I believe, would get me everything that I need. So I think that's the range that I need. I went 2 columns too far, so I'll delete those. And down to the bottom, and that's 1996, correct. Okay, so what I want to do is create a fitted value from what's up here. and a residual. Okay, but the fitted value is easy. Okay, that's just the intercept in B18. Okay. And if I really wanted to I could say it's B18 times F21 and copy that one down, but since the column F is all ones, I don't really have to do that. And then my residual, okay, is then the fitted value in G21 minus the actual value in E21. And I can copy that down, and I get like so. And I've done this incorrectly. I coded my residual backwards because these two should add up to this one over here. So that's a useful mistake in the sense that just see me making a coding error, and you learn how to fix them, okay, just by inspecting things. That still doesn't look right. What is going wrong? Oh, I think I still have a minus sign in front of there. Tricky. There we go. Okay, and then let me format this column with one of my custom formats down at the bottom, which is going to make this somewhat easier to read. And doesn't look like I actually have a nice one down there, because custom formats can be a little bit snaky. So let me put one in. And this still doesn't look great. Not sure exactly what it's done here. That should look pretty good. I don't think that has to have a number symbol in front of it. Nope, that was definitely wrong. I think maybe my problem is my font here. So I'm going to go back to the custom format I had. Yeah, somehow, gosh, Office does love those Arial fonts. And people who do spreadsheets hate them. So I'm going to switch over to Consolus, which looks a lot kludgier, but is definitely easier to get information out of. Okay, so everything's stacked up there. It looks nice. And again, what I want to do is eyeball this against known recessions and make sure that I get negative shocks around recessions. So Great Depression looks good here. Negative shocks, little uptick in the mid-30s, another negative shock in 37. World War II is really strong. Going down to the end of the data set, 1990 is a recession year, we get a negative. 1982 is a bad year, we get a big negative. 80 was a bad year, we have a big negative. 75 and 74 were bad years, we have big negatives. So this looks really, really good. Okay, so these are our estimates of the impulses or shocks that are hitting the economy. Now, the thing is, if we go back and compare to case 3, with case 3, our coefficient was extremely close to 1, so the residuals we would get would be in the same range, okay, as forcing it to be 1, which is what I did over here when I made the dependent variable the difference logs instead of the actual log. So I'm going to copy these residuals from case 3 over here to case 4 and put them right there. Okay, and let me get those that nice format that I just developed. That makes it easier to eyeball them. Okay, and we'll do that. And of course it still doesn't look great, which is not nice. And that's because it's still got that dollar sign in there. Change that back to a question mark and they should stack up nicely. Okay, so these are case 4 and these are copied from case 3. And I expect them to be really, really close, and they are. Okay, that one's off in the 3rd digit, that one's off in the 3rd digit, that one's off in the 3rd digit, and so forth. So to the extent to which I can interpret those difference logs as growth rates, the first one there is something like 12%. That's the difference between 12.3 and 12.6%. So we're differing in the tenths digits in growth rates. Okay. Now, go down to the bottom here, and again, we have differences of, 3/10 of a point, 4/10 of a point, something like that. They're not large differences. Okay. So I don't actually need these case 3 residuals anymore, but I wanted to put them on here for comparison purposes. Okay, so case 4 looks pretty good here. Now, one of the things that I want to talk about is an excellent thing that we need to talk about in terms of COVID-19. Okay, if I look at these residuals and think about them from a statistical perspective, we should readily conclude that this looks like there's heteroscedasticity. Now, heteroscedasticity is where there's a pattern in the residuals where they're related to the underlying variables in some way. And if I look at this, I've got them really, really big and negative at the beginning, really, really big and positive during World War II, and then much, much smaller for the rest of the series. So this definitely seems like heteroscedasticity. Okay? Problem with that, jumping to that conclusion that this is heteroscedasticity, is that correcting for heteroscedasticity is kind of like assuming that the residuals that you have are actually incorrect in some way, okay? That they shouldn't have that pattern at all. But that presumes that you know that the pattern that you're seeing shouldn't be there. But what if it's a truthful pattern that should be in the residuals? I hit the F1 key by mistake, so let me close that window. Well, why would that be relevant here? Okay. Well, I used this long data set and I included the Depression and World War II. And I know the Depression and World War II are unusual features of the data. If they're unusual features of the data, should I get unusually sized residuals? Well, the answer is probably yes. Okay. So if I look at these and say, gosh, these are really big between 1931 and like 1944, maybe that's heteroscedasticity. Maybe it's picking up something that really should be included. Now, you go back down to the end of the data set and you see the small size of these, and you'd definitely be inclined to say it's got to be heteroscedasticity. Okay, we haven't seen anything like that in 70, 80 years, right? Except, is that probably what we're going to see in Q1 and Q2 of 2020? We don't know much about what that data looks like yet, and we're really not going to get a good sense of what's going on in the economy now until probably midsummer, after this class is long gone and over. But I think it's entirely plausible that for the first time in 80 years that we are going to get a residual in this range of, say, minus 10% here. And so those things that we thought from the Depression would never happen again may have just happened. And the thing is, if we had treated them as heteroscedasticity and gotten rid of them somehow or modified our results in order to avoid them, we would have lost any richness of detail about what happened in the Depression by basically using a statistical method to get rid of something that's historically important. Okay? So I think this is, amazing and huge that I've been using this annual data set for several years, and now it's going to have big residuals at both ends of it. Okay. Because could I have used the quarterly data set that started in 1947 years ago when I wrote the handbook? I could have. I thought about it. But what I thought is there's too little experience in time series where people are told use the longest data set possible, even if it doesn't have a lot of observations in it. And I figured this was a good opportunity to push on students the idea of include the Depression and include World War II in your data because sometimes it's going to make a difference. And I think maybe it is in this class or in the regressions like this for the class next year. Maybe not for you guys, but definitely for next year. Okay, so anyways, we don't have that data yet. Let's think about the data that we actually have, and let's go down to the bottom here and take a look at these shocks and try to ballpark what the size of them actually is. Okay, so going over here, I actually need my labels. My log of annual GDP is in this column C right here. So it's 9.308, okay, in 1996. And my residual is 0.003. So that means, okay, that the scale of that residual can be figured out from the scale of this 9.308 over here. So let me go over here and reverse that log and take the exponent of C87. Oops. And recover my real GDP for that year, which was about $11,000 billion. Now the size of the residual here is 0.003, okay? So that would be like having this be 9.305. Now this is never a calculation I want you to do really ever again. I'm just using it to ballpark in real dollars what that 0.003 is. In actuality, the model is going to have some propagation mechanism in it that's going to take all of these residuals and mutate and expand them into larger things. So I'm just trying to get a sense of what the initial shock is, but not what the overall shock is. But let me click enter on this, and we find out that a difference of 0.003 with the scale of numbers that we had in 1996 is in the range of $40 billion. Okay, so a typical shock in 1996 was $40 billion worth of GDP. Now that gets, as I said, amplified and mutated into the changes that we actually see, which might be quite a bit larger than that, 2 or 3 times as large. But $40 billion is the underlying source shock. Okay, so this minus 0.008 is probably something like a minus $90 billion shock, and this might be a plus $55 billion shock, and that might be a minus $60 billion shock. Basic idea is that those shocks are not that huge compared to the entire economy. The entire economy is like $11,000 billion here, and it's getting hit by shocks of size 40. And that's causing what we experience as business cycles. I'm saying that now to put that in perspective with COVID-19 because now we're in 2020 and our GDP is about $20,000 billion. And do you really think that we were hit by a $40 billion shock this quarter when we have a $20,000 billion GDP? Or do you think that when we actually get the data and measure it, that the size of that shock is likely to be something like a $500 billion shock this quarter? I don't really have any idea, but I think that that is a plausible shock for what we're seeing. Okay. Certainly if I came up and did this in July when we got the data and came up with a $500 billion shock, I wouldn't be surprised at all. Okay, so now that I've got those, I want to delete those because that was just kind of a test calculation there. Okay, and I want to wrap up what I want to say about case 4. And so here's the thing with case 4. If I look at these residuals, I definitely want them to match up with recessions, and they do. Okay, but they also show a little bit of serial correlation. Serial correlation is the idea that the residuals are correlated with each other across time. And in time series, we're really concerned about autocorrelation, the correlation of residuals with themselves at different points in time. And we're concerned about positive autocorrelation, the idea that the economy seems to be hit by several positive shocks in a row, producing an expansion, say. And I just don't think that that's in the nature of shocks, that they're kind of always going in one direction or the other. So if I eyeball this set of numbers here, okay, let's take a look at, say, the 1980s, okay? This was a period of a good long expansion here. 83 to 89 are all expansion years. And it's pretty cool that we got some negatives in the middle there, okay? But there's definitely some serial correlation in the sense that they hung positive for 3 years, then hung negative for 2 years, then hung positive for a couple more years. I'm going to go back and do the same thing in like the 1960s here, another long period of expansion here. Okay? And again, what we see is several years in the middle there of continued positive shocks. Okay? Now, 62 to 66 were pretty good years for the economy, but do I think that the shocks were positive every single year? That seems implausible. Okay? But if we keep going back, we keep seeing that same sort of thing. Here's a run of 4 positives in a row. Okay? Here's a run of 6 positives in a row during World War II. Here's a run of 4 negatives in a row during the Depression. Here's a run of 3 positives, 4 positives in a row during the Depression. I think this should be a little bit choppier than it actually is. Okay? And in time series, your instinct should always be, when faced with the possibility of autocorrelation, is that you do exactly what we did when we went from case 1 to case 2. Okay? Case 1 had a pattern in the residuals. We were concerned about it, and the way we solved it was by adding a lag-dependent variable. And then case 2 was an improvement over case 1. We're going to do the same thing to improve case 4. I'm going to add a lag-dependent variable to the right-hand side, and that's going to be my model for case 5. Except the dependent variable that we're using here is now the differenced logs of real GDP, and that's growth rates. Okay, so we're going to put a growth rate on the left and a lagged growth rate on the right and estimate case 5. This video is now over 20 minutes. This is way long enough, so let me leave you for right now on this note, and we'll come back on another day. Bye.